X3DOC is an acronym combining X3D and doc for documents, because it uses X3D descriptive language as a base to combine 3D and two-dimensional design in a single format, to have all in 3D model documents and animated shapes. So X3DOC is basically a textual format in XML, like SVG. It is based on X3D for the base data format, and for SVG for the two-dimensional graphics. Currently, the X3DOC standard can be used with an encoder producing files from existing SVG or PDF files. So you don't have to learn actually the language, because the translator produces the format from existing documents. And when you have the document in X3DOC format, you can view this document with the viewer, and this presentation is currently using the viewer. So X3DOC can be used with SVG files designed with other tools like Inkscape or Adobe Illustrator. And you can also import PDF files generated from GhostScript or Acrobat or the Office software suites. So it is not a language for authoring, it is a language for visualization. And authoring tools are very complex, and we reuse existing authoring tools so that designer can keep the tools they use today and produce X3DOC content. X3DOC can also import existing files from computer-aided design, like the design of machines in manufacturing, and put the machine design in a web interface, if the web interface has X3DOC support. So this presentation starts not with X3DOC actually, but with a summary of the technical evolution, a separate evolution of two-dimensional and three-dimensional graphics. Then I will compare the different standards and justify the combination in X3DOC, and then I will show how it can be used on the University of Utah in the United States. This university had a computer science department in the 60s and 70s, and this computer science department hosted the main researchers and entrepreneurs of the industry. So, for example, in this university, applications and vector graphics were then used for wireframe rendering, and the name vector graphics was a synonym of wireframe rendering until Adobe reused the same word, but initially they were three-dimensional. So Mr. Warnock had left the university in the 70s, but meanwhile, in the University of Utah, other students were inventing 3D technology. the 3D technology, in fact, was just an extension of the 2D technology object. But the smooth object has a base skeleton. The skeleton is just made with a few points, like SVG curve is composed of control points. You have a few control points for a complex shape, and the shape itself is completely described by the control points. So X3DOC here shows the combination of the 3D model and bitmap image behind it, showing the initial design of the teapot by a student in the Utah University. And then you see the same in 3 dimensions. So it shows the extension of 2 dimensions to 3 dimensions, and then the close relationship between both systems. After the research phase, the industry started to produce commercial application, and the main companies in graphics were Adobe and Silicon Graphics, both founded the same year by 2 former students from Utah University. The first was John Warnock, student in the end of the 60s, and the second was James Clark, student during the 70s. So their personal story is nearly a parallel story, because you find at the end SVG as a result of Adobe, and it led to the current situation with SVG. After developing web standards, both Adobe and Silicon Graphics abandoned the project before the success, in fact. Adobe abandoned the SVG plugin in 2005. Silicon Graphics abandoned VRML, both SVG and X3D on your browser. Illustrate the separation between 3D and 2D. Just before the VRML standard was defined, the company Silicon Graphics was already producing 3D maps like this one. This is not an actual map, it's just a screenshot taken 20 years ago, a screenshot of the Open Inventor tool from Silicon Graphics. But this tool could have been used for maps currently if the standard had been designed for vector graphics. So this design on the left is made with just the extensions of X3D, the extensions of X3DOC. So currently, X3D has extensions for vector graphics, but it's not consistent because many organizations are specifying extension without a common format. So X3D two-dimensional extension exists. They are defined by the Web 3D consortium. The base two-dimensional graphics are defined by the W3C consortium for SVG. The two-dimensional graphics from video and 3D combined in CAD on the MPEG-4 standard has also 2D graphics extension looking like an intermediate between X3D and SVG. Extension to X3D. And you could be interested in discussing about choosing SVG or X3D as a base. And I chose X3D instead of SVG, and this page explains why. So SVG on the left, because SVG depends on SVG depends on the Adobe format. I don't remember the page here. And X3D depends on the Silicon Graphics standards. So X3D has already a data model very suitable for hardware acceleration. X3D has a three-dimensional geometry matrix. X3D also has a descriptive specular, ambient, and other colors. So I used the existing file formats to produce the new X3DOC format, combined also with SVG output, in order to fill the gap between two-dimensional visualization and three-dimensional visualization. I have a common output for both formats using the same input. So you can translate an input. To illustrate this, I will show it on the next slides. The translation has many cases. So the first case is to produce SVG company in 2006, and here this clock is in a three-dimensional environment. So the clock is flat. You have the shading system of OpenGL when the when the scene is rotating. You have the shading of OpenGL reducing the light on the flat scene, combined with the shading of the gradient in OpenVG. The gradient in OpenVG are exactly OpenGL. You have also the complex gradients of SVG working in X3DOC here. And gradients defined by Adobe Photoshop, not implemented in SVG like the radial gradient or angle gradient. It is very simple actually, and it could be in the SVG standard, but it is not. So this case is to translate OpenVG to portable SVG working on any browser, or X3DOC working in a three-dimensional environment. Second case, you can import in a three-dimensional system existing graphics designed in SVG format. So I took a map. This is the second map of the Netherlands. The first one was the example from Silicon Graphics I showed before, and this one is exactly the file from Wikipedia translated to X3DOC without any change except the viewpoint, so that the scene is slanted. You have the viewpoints for the front view here, and the viewpoint from the inclined view. In the same file, you can add it after the translation and show details with these viewpoints. In the X3DOC system, you have also scene picking system, similar to the SVG mouse events. So you can see the elements composing the design made with Inkscape, and the name of these elements on the top of the scene. So you can also have handlers taking the event to show additional data when you click on a specific part of the scene. So this is an example of SVG of medium office documents, and this presentation, for example, was designed with a well-known slide making tool and translated to X3DOC using PDF format. So I printed the file from the slide maker as and to illustrate the system, I show here a very old scene taken in the 80s. The scene shows the founder of Adobe and a Macintosh behind, and PostScript design on a frame. Actually file available with GhostScript as a PostScript file, and you can translate the PostScript file to X3DOC and put the result over the picture at the place of the bitmap image, and have exactly the same rendering. And on the picture, the original image is distorted, so you can also distort the frame of the imported image included in rectangular frames. You can also combine them in non-rectangular frames. So you can build nested PostScript file included in a second SVG file containing the bitmap image, and itself is contained is the presentation, and the presentation itself is contained in the container of the viewer. So you have 4 levels nested. The viewer can also render movies. just like you can integrate movies in HTML browser with a Flash plugin. So YouTube is actually a Flash plugin, and you need Flash in your browser to use YouTube. And I have developed a small viewer combined with X3D to have the movies from YouTube in an X3D environment. So you can take any movie on the YouTube and put it inside a 3D scene. The 3D scene itself is flat for the SVG-like part, and in volume for the pure 3D part. So the viewer, in fact, is a 3D scene. You have control here, not as a flat shape, but as a cylinder, in fact. The buttons are also in 3D, but you don't need to redevelop the viewer. This is a standard viewer you can reuse for any movie taken from YouTube or movie made by yourself. And you can also have the viewer in a separate window and play the same movie or different movie. And you have also possibility to view the same scene in separate synchronized windows. So this is just to show that it can sustain multi-threading with no problem using OpenGL and hardware accelerated graphics. All this system consumes very low CPU, high resolution movie. So you have the highest standard currently, and it consumes half of the power on this PC because I have something working in the background. But on my desktop computer, it consumes less than 20%. So X3D is an alternative to the software rendering, because the hardware rendering is very efficient for complex rendering. So this presentation depends on hardware, and many examples given in this conference deal with the software versus hardware rendering, and hardware is considered as not reliable if your hardware is not very recent. So this viewer for X3DOC is designed to comply with old or recent hardware with large or small hardware. The only requirement is OpenGL. We can use OpenGL conventional pipeline on OpenGL embedded systems. You have the same result. For example, you can view this presentation on a Raspberry Pi computer. This computer has a GPU and a CPU in a very, very small circuit, the same as in your mobile phones, actually. So the hardware is very, very different, but X3DOC has the same rendering on old and current hardware. Because you can render vector graphics with OpenGL, actually. OpenGL is considered as bad for vector graphics, but when you have a library producing the path, the basic graphic path in OpenGL, you can do nearly all the SVG rendering with OpenGL. So for example, this is a well-known SVG sample of the basic shapes rendered in a 3D environment without needing OpenVG. Is pure OpenGL. And the advantage is to have the extruded scene, because OpenGL works in 3D. Another example is the text fonts. This is a TrueType font using fill and stroke parameters like in SVG, but the stroke parameters have also depth, so you can have the border extruded. And you can also use the path, the SVG path, to produce 3D models using the extrusion defined in the X3D standard. The X3D standard can make an extruded part with two planar surfaces, not two planar, a planar surface for the section and a second for the spine. Here the spine is a SVG path in 3 dimensions, and the section is another SVG path. So combining both SVG paths in 3D can produce 3D objects. And you don't need OpenVG extension, you can just use OpenGL. X3DOC also includes the possibility of path rendering proposed by NVIDIA. For example, yesterday you had a demonstration from Mr. Trivet from NVIDIA, and Mr. Trivet was presenting the work of Mark Kilgard from NVIDIA, and Mark Kilgard developed an extension of OpenGL for top and embedded systems. So, to begin with, nearly all the graphics standards today come from a single place. John Warnock, the founder of Adobe, was a student in 1969. Then, after his studies, he worked in a company owned by a teacher in the university. The company was owned by Ivan Sutherland, and the company was producing vector graphic terminals for professional, the same word for 2D graphics on a printer, actually. So the vector graphics currently concern the two-dimensional world, and to illustrate this, the well-known teapot is based on Bezier polygons, just like Bezier curves in two-dimensional graphics, extended with a third dimension. So the teapot is smooth. The initial design was a handwritten paper, and you see on the paper the control points 3D as a result of silicon graphics. At each stage of the development, these companies made things in 2 dimensions, 3 dimensions, with somewhat synchronized evolution. For example, Adobe developed the SVG standard for the web. Silicon Graphics developed the VRML standard for the web. But unfortunately, these two companies missed several opportunities to define a common standard in conference like this one, on X3D, in other conferences on Web 3D graphics. Both have separate audience, separate developers, separate data. It's a shame. And then development. But in fact, it was very good ideas, because currently SVG has a global success. And X3D, not known in this conference, has also a success using WebGL, just like the 3.js package described in the previous conference. But WebGL is used not for programming, but for rendering objects in X3D format with the X3DOM toolkit. This toolkit can be downloaded on a browser and render a 3D model in X3D format without any plugin in your browser. So you can currently view TV, for example, when you have the program for a TV show under your screen, sometimes it uses MPEG-4 standard. And last, you have the Chronos Group. Chronos Group is the successor of the OpenGL Architecture Review Board. And Chronos specifies independent vector graphics. You saw yesterday the vector graphics proposed by NVIDIA, NVPR path extensions, and there are also extensions named OpenVG, extensions for hardware accelerated rendering. And all these standards are not linked together by a common committee. This is the reason why I made my own language for the parameters of materials and lights. So you can have a standard way to define lights and materials. For example, in SVG, you have one color, fill or stroke color, but in OpenGL, you have the diffuse of the Gouraud shading system. So you don't invent anything when you take X3D as a base, because X3D already has these colors. And when you produce documents for 3D world, you just fill the diffuse color like you fill the fill color, like you define the fill color in the SVG. SVG is a subset of the material in 3D, in fact. There are also other advantages, but it is very technical. Prototypes and routes. Routes are the same as events in SVG. Routes are easier for large event interactions, because routes is a basic wiring system, so you can combine many routes and your system don't crash, and it's easy to debug. So document in PDF into an output document is SVG, or an output document in X3DOC and have the same result on screen. So you can visualize a two-dimensional graphic in a pure flat environment or in a volume environment without any difference. Or X3DOC from a program developed for the OpenVG standard. OpenVG was specified in 2005, and you can find on the internet demonstration for OpenVG working on a dedicated hardware with the OpenVG library. So you cannot visualize as OpenVG program on your PC if you don't have this hardware. On the opposite, you can put the OpenVG program as the input of this tool and produce a SVG or X3DOC document similar to the output of OpenVG. So for example, this clock exists as an OpenVG program. It was developed by the Amanit the same as is SVG, as in SVG. So you combine here a shading system using gradients and a shading system using complexity translated with no manual operation to this 3D format. But the most general case is the PDF data from PostScript file. Then the PostScript file was translated to PDF with Ghost Script, an open source project. And then the PDF file was translated to X3DOC to have the result you see here. And this design is PostScript file to fit on your scene. So you can combine documents not only as representation, like you can include an image in SVG, and this image can include also a second image. The scene here, for example, combines one. For example, here you have using the X3DOC standard is an alternative to OpenVG vector graphics named NVPath rendering. And in 2012, Mark Kingard presented some examples of his work at SIGGRAPH, and this example showed the advantages of OpenGL extensions from NVIDIA. Sorry, it's an automatic system from Windows for very EV graphics. And one example of EV graphics was the design of a girl with letters. So this is a very EV SVG file, but it is easy to render it with OpenGL and have high resolution with no difficulty. And actually, this is tessellated in OpenGL. So you can switch the rendering mode to show the tessellated format. In fact, all is made with OpenGL triangles. But the difference is that the rendering here does not require programming, because I used the PDF file from the girl as an input, and it does not require recent hardware because it works here on a ATI GPU, not from NVIDIA, so it's portable. And Mark Kilgard also presented a scene combining Tiger, the Tiger from Ghost Script samples, and Teapot, the Teapot from Utah University, and fonts from your PC. It is a true type font, and gradients, because the font is filled with a gradient. And in the NVIDIA demo, this scene was a program. It was a program in C language or in C++, and you can download the program from NVIDIA website. But here, it's not a program, it's a file in X3DOC format. So the advantage of X3DOC is to provide the advantage of recent OpenGL extensions on non-NVIDIA hardware, and to have complex scenes mixing 3D and 2 dimensions without programming. Another application is, in fact, the reason why I developed it is to combine 3D models from mechanical design and pages to make a user interface. And when you work in automation, for example, you cannot reuse the 3D model you have in the design department for operator interfaces on the factory floor. So it's interesting to include a 3D model in a multi-page user interface so that you can develop the operator interface and design the machines at the same time. You don't need to have a designer for the machine and a designer for the user interface. You can have a single person working on both projects. And the model from CAD can be combined with vector graphics. The vector graphics can include the button in 3D and have behavior similar to common user interface, but it is not depending on operating system, because this technology is based on OpenGL embedded systems, and it works, for example, on a small machine like a Raspberry Pi. I tested it last month on a Raspberry Pi, so it's a very small computer on a very small GPU, but the GPU is sufficient to have a 3D model on the 2D user interface on multiple windows, all working on a screen without any window system. So you don't need Windows, you don't need X3 like a Linux system. You just need OpenGL and X3DOC viewer to have a rendering system embedded in technical application. And you don't need to design it with programming like with 3.js. You can import the design of the 3D model from a CAD model, a CAD model of a manufacturer, or from your own model designed with SolidWorks. I have killed the whole application, so I jumped to the last slide because I was just at the end. So when you integrate the system in a real application for control, you need to manage the computation time requirements. And in a simulator, computation time doesn't matter. So this is a simulation. But in a real system, you need to have very short computation times. And totally hardware acceleration produces interesting results because, for example, the previous example on the previous slide, I jump on the previous slide, I open the window, and I jump to the last slide. Voilà. It runs on a Raspberry Pi with a display cycle of 40 milliseconds. So it's compatible with the user interface. I think it should not be possible without hardware acceleration. And when you have a more complex model, so the model of the previous example had 20 parts moving. If you have 100 parts coming from a SolidWorks model, even on a Raspberry Pi, the display cycle is 100 milliseconds. So combining two-dimensional and three-dimensional graphics with hardware is accessible even on low-power GPU, like the GPU of a Raspberry Pi. The GPU is actually a mobile phone GPU. So I showed the different possibilities here, and you have additional slides in the PDF version, and you should be able to download it after the conference. So the system of X3DOC is versatile, and I hope it could become an extension of the existing X3D standard. So I finished.